The impossible discovery. Everything we thought we knew about cosmic history just collapsed. For decades, astronomers calculated it took billions of years for the universe to build mature galaxies. James Webb just found fully formed spiral galaxies existing just 325 million years after the Big Bang. That's not just unexpected, it's theoretically impossible under our models. This is how the James Webb Space Telescope is forcing us to rewrite the entire history of the universe. The old timeline, a story that seemed settled. Before the James Webb Space Telescope launched in December 2021, the cosmic story seemed settled. The Big Bang occurred 13.8 billion years ago. For the first few hundred million years, the universe was too hot for anything but hydrogen and helium. The first stars took around 100 million years to ignite. Galaxies needed at least 500 million years to assemble into anything recognizable. Massive structures like galaxy clusters required billions of years to form. It was a slow, methodical construction process, or so we believed. The foundation of our understanding. This timeline wasn't guesswork. It emerged from the Lambda CDM model, decades of observations from Hubble, and computational simulations that modeled galaxy formation step by step. Every piece of data seemed to confirm it. When astronomers looked at the distant universe with Hubble, they saw exactly what they expected: primitive, chaotic structures gradually organizing over billions of years. The math worked. The physics made sense. Teams published papers that all pointed in the same direction. But there was one problem no one fully appreciated until recently. Hubble's blind spot. Hubble's vision, powerful as it was, had a fundamental constraint. It primarily saw visible and ultraviolet light. The most distant ancient galaxies had their light stretched by cosmic expansion, redshifted into infrared wavelengths that Hubble simply couldn't capture. We weren't seeing the full picture. We were seeing a filtered version and mistaking it for reality. The early universe was hiding secrets that only infrared eyes could reveal. A revolutionary new eye on the universe. James Webb doesn't just improve on Hubble, it operates in a fundamentally different realm. Its 6.5-meter mirror collects more than 6 times the light of Hubble's 2.4-meter dish. The real revolution is in what it sees. The telescope is engineered for infrared wavelengths between 0.6 and 28 micrometers. This allows it to pierce cosmic dust that blocks visible light and capture photons that have been traveling for over 13 billion years. Light from galaxies that formed when the universe was barely 3% of its current age. Opening the cathedral doors. If Hubble gave us a keyhole view of the early universe, James Webb threw open cathedral doors. Where Hubble saw darkness, Webb sees galaxies. Where Hubble detected formless blobs, Webb resolves spiral arms, galactic bars, and complex structures that shouldn't exist yet. It's not just seeing farther, it's revealing what was always there but hidden from view. And what Webb found immediately started breaking the rules. The first bombshell, JWST. When the telescope turned its gaze to the universe's first billion years in 2022, astronomers expected to find proto-galaxies, small and messy, barely holding together while forming stars. What they found instead defied every prediction. Take JWST, a galaxy discovered by the JWST, Advanced Deep Extragalactic Survey. This object exists at redshift 13, meaning we're seeing it as it was just 325 million years after the Big Bang. This isn't a faint smudge of primordial stars, it's massive and organized, showing efficient star formation with signs that hundreds of solar mass stars had already lived, exploded as supernova, and enriched the surrounding space with heavy elements. A timeline that doesn't add up. Structures that, according to existing models, should require at least 2 billion years to form. Yet here it is, fully assembled in just 325 million years. The timeline doesn't add up. This means one of several things, all of them revolutionary. Either stars formed faster than physics currently allows, or the first generation of stars was fundamentally different than we theorized, or dark matter behaved in ways we don't yet understand, or some unknown process accelerated galaxy assembly by a factor of 5 or more. None of these options fit comfortably into current cosmology. 800,000 galaxies in a broken model. Then in June 2025, astronomers released a map showing 800,000 galaxies across cosmic time, revealing 10 times more galaxies at extreme distances than models predicted. These aren't just more galaxies, they're showing up with barred spiral structures, the kind of organized features that require stable rotation and billions of years of settling. But Webb found them in galaxies that formed less than 3 billion years after the Big Bang. The universe was building complexity on a schedule that breaks every simulation we've run. The black hole crisis. The galaxy problem was just the beginning. Supermassive black holes presented their own timeline crisis. These cosmic monsters, millions to billions of times the mass of our sun, shouldn't exist in the early universe. Black holes grow by consuming matter and merging with other black holes. That process is limited by physics. A black hole can only consume matter at a certain rate before radiation pressure from the infalling material pushes new gas away. This is called the Eddington limit, even feeding at maximum theoretical speed. Starting from a stellar mass black hole seed of maybe 100 solar masses, it should take several billion years to reach supermassive scales of 1 billion solar masses or more. Black holes that shouldn't exist. James Webb discovered supermassive black holes, fully grown at redshifts beyond 10. That's less than 500 million years after the Big Bang. Black holes with masses reaching hundreds of millions of solar masses, existing at a time when they theoretically shouldn't have had time to grow past a few thousand solar masses at most. One example is a black hole found in July 2025 that astronomers think formed through direct collapse. Instead of starting as a dead star, this black hole condensed directly from a massive gas cloud, skipping the stellar phase entirely. Direct collapse black holes, a theory that was speculative until Webb made it a necessity. The mystery of little red dots. This brings us to a peculiar class of objects Webb discovered called little red dots. First spotted in 2022 data, by August 2025, the telescope had identified 300 unusually luminous red sources in the early universe. These compact objects, some just hundreds of light years across, appear at redshifts between 4 and 8, corresponding to when the universe was 600 million to 1.5 billion years old. They emit broad emission lines, suggesting gas moving at extreme velocities, but they produce minimal X-rays, which is strange for active black holes. Cause and effect reversed. Some of these little red dots harbor black holes with 50 million solar masses dominating their tiny host galaxies. The black hole represents 10% of the galaxy's total mass. Today, supermassive black holes make up only 0.1% of their galaxy's mass. This inverts everything we thought about galaxy and black hole coevolution. The standard story says galaxies form first, then black holes grow in their centers over time. Webb is showing that black holes may have formed first, possibly from those direct collapse events, and then shaped the galaxies around them. Cause and effect reversed. The chemistry problem. The timeline problems extend beyond structure to chemistry. Heavy elements like oxygen, carbon, nitrogen, and iron don't exist at the universe's birth. They're forged in stellar cores and scattered by supernova when those stars die. This process is generational. First-generation stars, called population 3 stars, would have been massive and metal-free, made only of hydrogen and helium. They live fast, maybe just a few million years, then explode. Their supernova enrich the surrounding gas with the first heavy elements. Second-generation stars formed from this enriched gas, live their lives, die, and enrich the cosmos further. Astronomers calculated this enrichment cycle could take at least 300 million years to produce significant amounts of elements like oxygen. Oxygen where it shouldn't be. James Webb detected strong oxygen emission lines in galaxies like JWST 13, the same one mentioned earlier, at just 325 million years after the Big Bang. Oxygen levels suggesting multiple stellar generations had already completed their cycles. The universe was forging, destroying, and recycling stars at a pace our models said was impossible. This rapid enrichment means either the first stars were far more massive and short-lived than predicted, dying in just hundreds of thousands of years instead of millions, or star formation was incredibly efficient in the early universe, converting gas into stars at rates we've never observed in the modern cosmos. A wholesale revision of cosmic history. Individually, each of these discoveries challenges specific assumptions. Together, they amount to be a wholesale revision of cosmic history. The standard model of cosmology, lambda CDM, has been spectacularly successful. It accurately predicts the cosmic microwave background radiation, the large-scale structure of the universe today, and the acceleration of cosmic expansion driven by dark energy. But it was calibrated on limited data. Observations that we now know were incomplete because Hubble couldn't see the full infrared picture. Fundamental parameters need revision. James Webb isn't just adding details, it's revealing that fundamental parameters need revision. Star formation efficiency in the early universe may have been 5 to 10 times higher than we assumed. Black hole seeding mechanisms clearly included direct collapse from massive gas clouds, not just stellar remnants. Dark matter distribution in the first few 100 million years must have been denser or clumped differently to allow such rapid structure formation. These aren't small adjustments, they're rewrites of core processes. Searching for solutions. Some astronomers are calling for modifications to dark matter theory itself. Others suggest the first stars were population 3 hypergiants, monsters with hundreds of solar masses that burn through their fuel in less than 1 million years, jump-starting enrichment far earlier than models allowed. Still others propose that feedback mechanisms, the way black holes and supernova regulate star formation by heating or expelling gas, operated completely differently in the early universe, perhaps allowing sustained bursts of star formation instead of the stop-and-go cycles we see today. The truth is, we don't know yet which, if any, of these solutions is correct. What we do know is that the timeline we taught for decades is wrong. Kapataro, the oldest structure ever? To understand what this rewrite means, look at an object discovered in 2025 called Kapataro, with the catalog designation Sears IDU 100588. This reddish source was found in images from the Cosmic Evolution Early Release Scientist Survey. If confirmed as a galaxy, its light comes from potentially 90 million years after the Big Bang, making it the oldest structure ever detected. But there's debate. It might be an extremely distant galaxy, or it could be a brown dwarf in our own galaxy, or even an early black hole accretion disk. The ambiguity itself is revealing. Webb is finding objects that blur our classification systems, forcing us to develop new categories and better methods to distinguish between possibilities. The race for answers. Right now, as you watch this, astronomers are racing to explain what James Webb is showing them. New papers are being published weekly, each proposing modifications to theory. Simulations are being rerun with adjusted parameters, higher star formation efficiencies, different dark matter properties, alternative black hole seeding scenarios. Some models are beginning to match Webb observations, but only by invoking processes we've never directly observed. Meanwhile, the telescope continues observing. Each new data release brings more early, massive chemically enriched galaxies. The sample size grows, the timeline crisis deepens. We're not approaching answers, we're discovering the questions were wrong from the start. A revolution in progress. The history of science is filled with moments when better instruments shattered comfortable assumptions. Galileo's telescope revealed Jupiter's moons, proving not everything orbits Earth. Hubble's observations in the 1920s showed the universe expands, destroying the static cosmos idea. James Webb may be this century's equivalent revolution. It's not just rewriting the timeline of cosmic history, it's forcing us to question whether we understood the fundamental rules of how universes build complexity. How long will this crisis last? However long it takes to build new theories that match what Webb is showing us. And given that the telescope is designed to operate for 20 years, this revolution's just beginning. The universe assembled itself faster and stranger than we imagined, and thanks to James Webb, we're finally seeing it clearly.